For these sections, I will talk about advanced applications, mainly for Isobaric labeling in MaxQuant and Perseus. I think during this summer school, we have been asked so many times about TNT. Hello? Is that better? Yeah. Okay, good. So that's why I said that during this summer school, we have been asked so many times about TNT normalization and then a lot of things. Okay. So in your current version, the TNT, when you run after running MaxQuant, the table you get is row intensive. It's not normalized one, so you have to do some other package like Lima or come back to remove the package. This is current solution. I will present to you the new developed methods for TNT labeling, and hopefully it will be released soon, and then you can know you can get our new methods, and then in this lecture, hopefully you can learn how to use it. Okay, what is Isobaric labeling? Basically, Isobaric labeling is a strategy for quantitative proteomics. Peptide or protein are labeled by various chemical groups, but they have the same identical mass. Okay, but varies for the distribution of heavy isotopes. So it's easy that we can really use this to identify multiple samples. So the advantage of TNT labeling is we can identify multiple samples at once. And then also can reduce the measuring time. For example, if you have 10 samples, you want to do mass spectrum of them, then in the previous way, maybe you need to do 10 times experiment. But for TNT, we can really reduce this measuring time for once. And then also, will not have no variability between runs. And then the two widely used Isobaric labeling is TNT and iTrap. More or less these two types are more or less the same, but the difference is their different chemical structures, so this makes some difference. And then TNT currently is much more popular because it can produce more multiplexings. I think this year they already announced maybe 16-plex will come soon. Okay. So this is the TNT structures. You can see these reporter regions have a cleavable linker, mass normalizer, and then peptide reactor. So basically, you attach peptides, and then we have different mass of reporter, and then use mass variance. They can keep every tag is the same mass. So what is the advantage of it? So basically, you can see this is the same mass, but after fragmentations, the reporter ion is different for each of these channels. So based on this, we can do quantification or identification for multiple samples. For example, this is 10-plex, so we can do identifications for 10 samples at once. So this is the flow chart. Basically, we have 10 samples, and then we put each of these samples with different plex. And then we mix them together with mass spectrometry. And then in MS1 level, because they have the same mass, so they are in the same place. But when we do fragmentations, we can start to see the difference. And then we can do identifications for multiple samples. So what the difference or what's the benefits for TNT labeling and label-free quantification for quantification part? This paper is published 2018 from Iggy's lab. They compare TNT and label-free for human and then yeast. So in their analysis, they found like the total identified protein in TNT is more than label-free quantifications. But label-free can identify more peptide. The interesting thing is the unique peptide actually is higher in the TNT label. So this means perhaps in label-free quantifications, some low abundance protein cannot be really captured. Okay? So this is their result. And then they also see that in the protein group level, more than 50% of the proteins will lose at least one sample value. But in TNT, they can recover it. And if they also do calculation, that's the number of proteins which have at least two values exist in the protein group level. In TNT, 2 times more than label-free quantification. So, and yesterday we heard a very, very amazing talk from Nikolai's. They use TNT labeling for doing single cell proteomics. So I just showed a picture of the same. Actually, they have the carrier channels. So each the other plex they can put single cell. And then basically they use this carrier channel, these informations, help the single cell signal can be recovered. Okay, so what is new in MaxQuant? Okay, basically we got this raw data from the machine, and then we put it into the MaxQuant to do analysis. There are two newly developed methods. One is Isobaric metric run. The other one is PSN level weighted integration normalizations. I will introduce this to you. And then afterward, we can load, perhaps, like putting group table to Perseus. And then Perseus also do something, some new plugins for helping to do TNT labeling proteomics data for the downstream analysis. For example, we can annotate like every labeling data at once. It's easy and simple. And also we can modify the channels. For example, in single cell data, you may not want to use the carrier channel for the analysis, so you can remove it. And then also we include more dimensionality reduction method. I think in the current version, you already can see we newly developed TSNE and UMAP for the clustering. Previous version, only PCA was there. Okay, I think Jürgen already talked about this. Perseus is a multi-lingual systems which we can make a bridge between C#, R, and Python. So basically, a lot of good statistic tools is originally written by R or Python. Now you can also use it in Perseus. Okay, before I tell you about the method, I want to introduce two data sets that we use in this study. The first one is from Josh Kunz and lab. Basically, they extract 8 different organs from each of 4 mice. And then they randomly assign these samples to different channels. You can see this the channel and then randomize it. And then repeat this experiment twice in different days. Of course, they use a little bit different data acquisition method, but we still can consider these more or less like a technical replica. So basically, they have 8 samples, 2 sets of technical replicas, and each technical replica has 4 biological replicas. Okay? And then, and then this one has no reference channel. All of them are samples. And then the next one have with reference channels. Basically, in this paper, they're trying to see there's a gene called PELI1. And then their hypothesis is PELI1 will influence the brain inflammations. So they inject EAE, which can cause brain inflammations, and then they take the samples from 0 days after injections, 10 days, and 20 days, from knockout mice and then wild-type mice. And then they have 2 replicas. And also, they assign the sample randomly. Okay. So we have 2 data sets, one with reference channel, one without reference channels. Okay, and now I'll come to the method. I think you also saw this picture already. It's measurement rounds. There's no identified, but here we identify, and then we can match that. Right? This is from the MS1 level. But TNT labeling is in MS2 level, so we have a new measurement round called Isobaric measurement round. Idea is also similar. You can see there's 2 rounds. I think MS1 level actually they look exactly the same. But if we could go deeply to check MS2 level, and then you will see in this green square, the signal is very unclear. But the other one, the corresponding one, here we have a clear signal. And then in TNT labeling, because we have barcode from the reporters, so we can easily to find, okay, which peptide is from which peptide. And we can increase the identified peptides for quantification. All right, does it work? We apply this method to 2 data sets, and you can see without using metric run with metric run, basically we can improve 30% of the quantification. This is extremely useful for single cell data. We can increase 70% to 100% for the quantification. But this small cell still can increase 30%. Okay, the other one is PSN weighted ratio normalizations. Currently, it's a lot of like normalization weight, but most of them is based on protein level. But we can imagine like PMT is worked on the PSN level. So if there is a way that we can normalize peptide in PSN level, that will be better, right? So basically, the idea is we ratio to the reference channel. If there's no reference channels, then we ratio to total channel. And then protein ratio will be weighted median PSN ratio. So what is the rate? Weight. Weight here is the number of ions selected for fragmentation. So this is the MS1 features. And then MS field time is for MS2 features. And then we weight it. And then the weight can be exponentiated. So basically, this means we can fine-tune this weight. So in order to get the best weight, then we use one data set, the judge-proof data set, to do the optimization. Easily, we just increase a little bit each time. And then you can see in 0.75, if we set this number as an exponent, then the median of the variance of protein groups is the lowest. So I think it makes sense, right? If the same protein across different samples, they should look similar. So the variance should be small. So if we set 0.75, we get best result. So if we apply these methods to the data set, this is the result. Before using normalization, you can see all these data points are grouped by the experiment. So we have two experimental sets. So they all group together. This we don't want to see. Okay. After using normalization, you see the point is start to group it by color. That means group it by the sample. So the batch effect was successfully removed. And then you can see that I didn't do anything for assign the batch information. Basically, if you use lemma or use combat, you need to give them which experiment or which sample, and then the column, and then the batch. Give them which batch is like how to organize or the order of the batch. But here we didn't do anything about the batch informations. It's still work. And then if we just look at one experiment, and you can see the data was grouped by the biological replica. After normalizations, they grouped it by sample. This experimental too is the same. Okay? And how about with and then for also check the variance. And then you can see after using TSN normalizations, the variance increased 50% to 8%. Okay? And then with reference channels, you can see without using normalizations, the data point is still grouped by the experiment. After using normalization, the cluster was disappeared. But we cannot see the grouped by the samples, right? When I saw this, I just have an idea that perhaps in 0 days, there are no difference because they just inject and then there's no inference shows. So perhaps it's the reason. So I removed these two samples, and you can see without using normalization, still grouped by experiment, we can see they grouped by the samples. Although it's still 1 point here, it's okay. And then if we remove 10 days, it's much more clear. Okay, only samples was grouped. And then we check the variance, you can see in 0 days, actually they are not really improved. 10 days still start to decrease a little bit. And then in 20 days, it's significantly decreased. So that means this peptide 1 genes, the influence of this knockout start to appear maybe after 20 days. Okay, so this is the result in current data right now. So because we have no tutorial to show you how to do this because the current version have no these functions, so I'll show you how to do this in screenshot. And then when you got the new version released, and then with these methods, you know how to do this. Anyway, it's quite easy. In the external version right now, we have another column here called reference channel. And then you can set reference channel. Okay? So basically, if there are no reference channels, you just add everything, all channels. For example, in this data set, we have 8 flags, so we assign 8 channels, all are used for the reference. But if you want your reference channel is channel 2 or channel 3, you just add channel 3. Basically, the index of the channel is based on the order of mass. So the one is 126, like this. And then in the group specific parameter, this is a type. And then you can select MS2. I think Naga already showed you yesterday. And then you can select which isobaric labeling you want to use. Just select it, and then all the information will list in this slide. And then there's a new options here called normalizations. And then you can select weighted ratio to the reference channel. Then we'll do the weighted ratio normalization in PSN level. And then you come to the MISC. There is a isobaric weight exponent, and you can change the value. This value is we train it by a geometric data set. If you have your own data set, you want to train by yourself, you can change this and then get the best weight for your data set. And of course, you need to assign the FASTA file for the mapping. And then click on this MaxQuant run, then they will automatically do isobaric MaxQuant run. And then you can start to run. And you got your output table. Okay? And then I will show you something new in Perseus. Of course, you load it in Perseus, and then you get all the information from cooking group table, and then you import which information you want to use. Normally, we use reporter ion intensity. Correct it, what? And then all this will be here. And you can see the matrix will load it, all the information. Okay, and then we can remove some unreliable protein groups like only identified peptide, reverse, or contaminants. Okay, this approach workflow you also will see in the afternoon tutorial for the basic process. Okay, this is something new. You can imagine if you have 10 samples, and then each sample have 10 EMT templates, then you have 100 samples, or 100 columns. And then you want to annotate these columns. And how can you do it? You need to annotate each one of them separately. Then you need it 100 times. That's a strategy, right? So what you can do, you just need to open your Excel and then put experiments. This is required, and then should be called experiments. And then here is channels, and also it's required to call channels. And then give them the name of the experiment that you set. For example, here we can see IDA 1, and then in your MaxQuant, when you design your experiment, there should be the same name here. And then Perseus can know which information they need to match together. And then give them a channel. For example, here we have 8 flags, so from channel 1 to 8. And then give them a sample. Okay? So now it's easy. You can just drag your tables and then copy paste. That will be easier. And then you just open here. There will be a new plugin in Perseus, and then there is called annotate from files. Then you just load the file. And then remember, use the consistent delimiter. Here I use tab, so you just do tab. If you have another delimiter, you can assign. And then it will automatically help you to do annotations. You can call example, you can call another one like other informations, more, and then will generate more annotation rows. Okay, and we also can remove some channel if we don't want to use it. For example, in dataset 2, we have a reference channel. Basically, we don't use reference channel to do analysis, so we can you can select samples here, and then just remove the reference, then the reference will come. Okay, and then we can logarithm these samples. I think it's easy. You just call here, basic, transfer, and then logarithms. Then we'll logarithm. And then we can filter out the unreliable protein groups that have a lot of missing value. For example, in this case, we use 70% as the cutoff. And then at least one group of the sample needs to match this material. Otherwise, we'll remove these protein groups. Okay, and then we can do the imputation. We keep default one, and you just come here as a default setting, replace missing value based on normal distributions, and then click OK. Then missing value will be replaced, will be imputed. Okay, and then there's two new dimensionality reduction methods just integrated in Perseus. In your current version, you already can see it. It's original from R package, so there's an R mark here. Okay? So you can install R and install Perseus R in order to make these two roundable. If you don't want to use it, fine, you can just easily to use PCA to do the classifications. But if you want to use, and then you can click here, and then you can see there's a lot of parameters you can play around. You can increase the number of components. I think most of you will change this, okay? And you need to see this button should be green. If there's a red, that means there's something wrong in your setting of your R or Perseus R. If you have any questions about this button, how to make it become green, you can come to us at the lunchtime can help you. And okay, just let you know if you run UMAP and TSNE is different as you run PCA. Because in PCA, it will directly plot PCA plot for you. But in the TSNE and UMAP, because it's original from R, you're still not able to transfer the plots to show in Perseus. So all we did is another way is we give you another matrix which contains all the information. So you can see there's a component 1, there's component 2. And then you can easily plot, scatter plot based on component 1 and 2, and then you can separate. So this is the result from UMAP. Much more clear. All the figure I showed you previously is all from UMAP because we tried PCA. It's also separated, but it's not such often separated just because of this. So you can play around and choose which method you like to use it. Okay, just final summarize this. MaxQuant and Perseus provide a platform for TNT data analysis. And then the Isobaric MaxQuant can use 30% for identify peptides for quantification. And the BSN networking organization can remove the back effect successfully. And then Perseus have some new developed plug-in for you to do a downstream analysis. Okay, any questions?